we can express the simplest case. So some of the case sites in your skin may stay in your skin for the whole of your life. And so we have a relation like this, which we call permanent specific relatedness. A specific case site is a part of your skin for the whole of the life of your skin. We all have brains, and so Todd's brain is a part of his brain for the whole of Todd's life. We do not yet have brain transplants. So this is an example of has part at all times on the instance level. Some case sites are parts of your skin when you're very young, but they die off. And so these would be temporary relatedness as contrasted with permanent relatedness. The problem is that some case sites are needed by your skin in certain parts of your skin, but this need is fulfilled by different case sites at different times. Now, this in machining would be where you have a machine which has very fragile parts which need to be replaced at different times in the course of the life of the machine. This is permanent generic relatedness. Now, in order to do justice to the switching in and out of parts, we need to distinguish permanent relatedness from temporary relatedness. And the problem is that OWL is not able to make this distinction. And so this is sometimes called silent change. When one case site changes to another case site, this is not represented in an OWL representation. And clearly, it's going to be an important phenomenon when we're dealing with changing parts in machines or in assemblies of products and so forth. Now, some background. We have processes, we have objects, and then we have one big process, which is called the history of an object, which is just the sum of all the processes occurring in that object over time. So the history is the biggest process in which you participate. There is one history for every object and one object for every history. Now we can represent permanent generic relatedness by using histories which have phases. And so phases have proper occurrent parts, and an example of a phase would be the phase during which a particular case site is part of your skin rather than another particular case site is part of your skin. They would be two phases in the history of your skin, and similarly with a machine part. So all the phases sum up to the history. If we can divide the phases into non-overlapping phases, then we can capture the difference between permanent specific relatedness and permanent generic relatedness. Permanent generic relatedness would be such that there is permanent specific relatedness in every phase. Now, the phases for our purposes would be, for instance, the phases in the product life cycle. So this is a simpler OWL presentation. Every portion of skin tissue in a human being is such that it has a history which has case site part phase. So we can write it all out like this, and we can do the same thing with a machine. All right, now, if we do this, then we solve the problem of transitivity for part of. We want to be able to say that if A is part of B, or if an A is part of a B, and a B is part of a C, then an A is part of a C. We can't do that because of generic partshood, where silent change of parts. We can't assume transitivity. This problem arises for part of. It also arises for located in. It doesn't really arise for any other relation, but there are combinations of relations which we need to keep track of, and to do the justice to those, we need to be very careful about the distinction between at some time or at all times, and more specifically for our purposes, at all times in a specific phase. It arises for location too. If A is located in B and B is located in C, then we want to be able to say that A is located in C. And when we have ships moving around the ocean, for instance, it may be that you're losing transitivity unless you're very careful for location also. All right, this is the definition of has continuant part of at all times in BFO 2020. So to say that B has continuant part at all times C is to say that B exists, for all times T, if B exists at T, then B is a continuant part of C at T, and for sometimes similarly. Now, we'll very rarely want to use this relation. We would want to use it for brains of humans. We might want to use it for certain essential parts of machines. All right, so an example from biology, baby teeth are a continuant part of a human being at all times during the childhood phase. If we express it using phase, we don't need to say at all times explicitly. This continuant part of during the childhood phase satisfies transitivity in a logically safe way. And those two relations are perfect inverses. So we can't assume perfect inverses if we're dealing with generic parthood. We want to assume perfect inverses for all kinds of reasons in OWL, and the at all times strategy allows us to do that. These are transitive, and we have proofs that they're transitive. This is the biological example using, first of all, the logic, and this is the OWL, which I certainly won't go into now. And this is a manufacturing example. So every machine during the assembled phase has a certain widget part. And this is transitive, and we have inverses and so on. Providing we capture the right phases, that's going to be the hard part here. But we would have to do that even without the part of relations in BFO 2020. Adopting BFO 2020 is not giving us any extra work. We have to do this work anyway. And this is the general template in Common Logic for what we need to do. And we will have a general template in OWL also. This is the first of the logic statement. And you can see how close it is to the part of at all times. This is part of during the assembled phase. All of the logic relating to the at all times relations worked out at great length in BFO 2020. We have something like 350 axioms, can be applied to the phase versions of the at all times relations. This is a definition we need for the template. This is one application, I believe, of the phase approach. A collaborator of Farhad, who has created a system for dealing with phases of products, process sequences using machine learning on intermediate product states. It shows how to define states in terms of certain characteristics, how you can define certain output states being products of certain input states, and so on. And I believe that this kind of work anyway is going to be directly relevant to working out the phase relations in the OWL version of the IOF. And now the conclusion. Why do we need BFO 2020 with temporalized relations? So phase problems only arise for certain kinds of entities. And for those kinds of entities, we can use the at all times relations in any case without hesitation. This is true for all of the at all times relations apart from parthood and location at, because there, for the other ones, transitivity does not arise. We provide them in BFO 2020 just in order to make the users of BFO 2020 aware that they are dealing with at all times relations. And in some circumstances, they may want to deal with at sometimes relations. And that facility comes free along for the ride. All right, but where the phase problems do arise, then we're going to need an overarching framework to keep track of all the phase subproperties and how to keep track of all the ways in which the part of subproperties interact with the located in sub and the combinations of these relations, potentially also with other relations that we need to assert. So it's going to be hard, but again, we need to do this work anyway. It's just that BFO 2020 gives you a framework for doing this, and it gives you a strategy for proving consistency for doing this. It enables you to define the templates for doing this so that once you've done it once, you will find it much easier to do it a second time because you can just use the same template.